Hey guys, welcome to another ACBR video. This video is all about how to program our robotic laser cannon kit. Now if you bought one of our robotic laser cannon kits and you're looking for a guide as to how to write all of the code, you are in the right place. But even more than that, if you're just looking for some guidance as to how to program servos or take in analog data from a joystick or control lasers or even like LEDs, you are also in the right place. This kit is a lot of fun. There are a lot of moving parts, and what's cool is it's not too tricky. So without further ado, let's get started. So this kit is a ton of fun. One thing I like about it is that there are lots of individual parts that in and of themselves aren't too complicated. But when you put the whole thing together, you get a really awesome final product. So if you have questions about how to build or solder up this kit, feel free to watch our build video. In this video, we're going to be talking about all about how to program it. So it's pretty straightforward. So with the Arduino, that's our microcontroller for this project. They're great microcontrollers. We're using this to pull in our analog data from our joystick, using that data to program our servos going back and forth and up and down, and then using one of our digital pins to turn our laser on and off. So it's really a lot of fun, and we're going to go through each one of these things individually. The very first thing we're going to talk about is how to use our digital pin to turn 5 volts on and off to control our laser. Alright, so if you have finished building your robotic laser cannon kit, you plugged the USB cable into your Arduino, the lights on the Arduino turned on, then you are ready to get coding. So without further ado, let's get started here. Now this window you see right here is what's known as the Arduino IDE, and IDE stands for Individual Development Environment. So this is where we can develop code. So what's so cool about the Arduino is that there are people around the world who've done so many different things with this. So the Arduino doesn't know anything until we write it some code. The Arduino can be, a high-tech toy. It can be a drone. It can be a robot, a robotic arm. In our case, a robotic laser cannon kit. But the Arduino can be anything. And there are so many examples of people all around the world building amazing things with Arduino. I myself am a huge fan, but that makes sense. But this is how we turn our Arduino into something else. We need to write some code for it. And so I think the Arduino IDE is a great tool. Now, there are alternatives to the Arduino IDE that some people really enjoy. I think when you're first starting out, this is a great way to get started. So the Arduino IDE right here can be downloaded from Arduino's website. I'll be sure to link in the description here anytime. It's free, and there's an amazing community around supporting makers and engineers and students, and really supporting them through creating things with Arduino. So there are also lots of tutorials in terms of downloading that program. Now, if you already have Arduino downloaded, I suggest updating. Right now I'm using the version 1.8.5, and that's not even the newest version, but you do want a newer version, especially if you bought one of our kits, because the Arduino Nanos with the built-in radios that we include, they run the newer bootloader. And so you will need a newish version of Arduino to have the new bootloader option. But other than that, you download it, upload it just like any other program, and then you have the Arduino IDE. So here, this program right here. The first thing I want you to take a look at here is these menus up here. So we have our Files tab, right? This is the exact same as every computer program ever, right? You can create a new sketch, you can save something or change the font size and, all that jazz. What I want you to focus on right here first is the Tools tab. Now, before we write some code, because obviously we want to get in there, write some code, get some data, build some robots. But what we want to do right now is to make sure we have a couple of settings correct. So, as a high school robotics teacher, there's a few things that I see my students forget all the time. And so I want to take just a minute before we write some code so that we understand the best way to get our program set up. There's a few settings that we have to make sure are ready before we can write some code that'll help us down the road. And so those are all found under the Tools tab. One thing that's really important is to make sure you have the right board type. Now, default in Arduino is the Arduino Uno, and the Arduino Uno is a really popular microcontroller. That being said, for this kit, we're using the Arduino Nano, and so you want to make sure that you have Arduino Nano selected. The next thing that is really important, if you are using an older Arduino Nano, which is fully compatible with this kit and anything else if you're doing this on your own, then you might have the older bootloader. But if you have an older version of Arduino, you're not going to have this newer bootloader. So if you bought one of our kits and you have a new version of Arduino, you can leave this alone. But if for some reason your code doesn't upload, if it errors out when you try to upload, then check this processor option. The 168, you're never going to need that. There's a chance you'll need the old bootloader if you have your own Arduino. But if you have one of ours, you're going to want to make sure this is staying right here. Now, this part is really, really important. I see students forget this all the time. So when you go to port, you have a couple options here. Now, more than likely, you're only going to have one option. I have a few here because I'm running this, my computer right now is a Latte Panda Alpha, and there's a built-in Arduino, so you can ignore these right here. You're more than likely going to have one number. It's going to say COM something, and that number might be different. And so all that's saying is, hey, there's something plugged in the USB port. Is that the USB port you want me to send code to? So whatever that number is, you want to highlight it, but you have to actually click on it. And you can check here. If you go over to the Tool tab again, you go over to port, you'll see there's a little check mark right there. Now, if you don't have that check mark, it's not going to upload. And it can be frustrating because your code can be right, but you try to upload it, and then it errors out, and you're like, oh my gosh, why isn't this working? You've got to make sure you have that check mark. So that's kind of a lot at the very beginning before we've even written some code. But what's nice is once you have these settings ready, you can just leave it alone. And now you can continue to upload code, you can change things. It's just really important that you have those things set from the very, very beginning. So once you have those things correct and that all looks in order, then we're ready to start coding. And again, if you have any problems connecting your Arduino to your computer or anything, shoot us an email. You can email me directly at matt@anyonecanbuildrobots.com, and I'm happy to help you. Our guide that comes with our kit also has a ton of help in terms of troubleshooting and stuff, but we're here to help. I'll just say that. Okay, now is the exciting part. We are getting ready to write our first code. So like we said, the very first thing we're going to do is start kind of small. We built this kit with people in mind that you could be just starting robotics or you have a little bit of experience. So if you've done some Arduino code before, this is going to be pretty familiar. But if not, don't worry. We are going to start nice and slow and then put everything together in a really, really cool package. So the very first thing we're going to do is test our laser. All right, so like we said before, the Arduino doesn't know anything until we tell it something. So if we want to use our laser, we're going to have to do what's called creating some variables. Now, there are these sections of Arduino. So there's the void setup. This is typically where you set things like inputs and outputs. You might establish some variables here, but this code, as it says right here, the Arduino will run this code once. And that's what you do to kind of set things up for your code. Now, there's a second section here. This is known as the void loop. And as it says in this comment, put your main code here to run repeatedly. The void loop, like it sounds, loops over and over and over again. So the main part of your code is going to live right here in the void loop. That being said, whenever I set my code up, a lot of times in data science or computer science, software engineers like to write their code as condensed as possible. And there's a time and place for that, but I like to set my code up a little bit differently. As a teacher, I want to make sure that whenever we're talking about code, that it's really, really clear what's going on. So my first step is moving this bracket down, getting rid of those comments. Anytime you see // those are just notes. So we don't really need this for our code to work. And I also like to put a few spaces above our void setup. So it looks like there's only 2 sections of code, like places where we'll put some code in between these brackets and in between these brackets. But in reality, we're also going to need to write some code above the void setup. We're going to do that here in just a second. So I would personally recommend getting your code set up like this. Not that it's the most condensed or efficient way, but it makes it really, really clear because all of our code has to live within these brackets. Otherwise, we can have an error. So let's get started. Like we said before, the very first thing I need to do is create a variable. So my first variable is going to be laser. Now, we did a couple things here. One, we talked about the data type. So this right here is just what kind of data my variable is going to be. Now, int stands for integer, and an integer is a number. Now, specifically, a whole number, negative or positive, right? Can't be a decimal or, a fraction. But in this case, the number 4 is referring to pin 4 on the Arduino. So all I've done is I've created a variable called laser, and I'm associating that variable with pin 4. So sometimes I like to translate this from English into robot. If I were to translate this, it would be something along the lines of, hey, Arduino, I have a new word for you. My new word is laser. Whenever I say laser, I want you to think the number 4. And the Arduino says, okay, cool, got it. No big deal. Laser equals 4, no problem. So we have a variable. Our variable is called laser. It is an integer variable, and we are going to be using pin 4 on the Arduino. All right, we have our first variable. So the next thing we need to do, like we said before, the Arduino can be anything. We can use it to drive motors, take in data from sensors, and do all kinds of crazy, crazy stuff, right? There's an infinite number of things we could do with this Arduino. And because of that, the digital pins on the Arduino, they can be inputs or outputs. We take in data with things like sensors and joysticks and buttons, and we're going to take in some joystick data later. But right now, we're trying to send 5 volts out of pin 4 to light up our laser. I love the laser diodes that come with this kit because all they take is 5 volts, but they're still pretty powerful. They're not dangerous, but they're more powerful than like little tiny laser pointers. And so they're really easy to program. So you could use this exact same code to program LEDs and lots of other devices too. But because these pins can be inputs or outputs, the pins on the Arduino, especially the digital pins, they're known as GPIO pins. And GPIO stands for general purpose in out. So they can be inputs or outputs, which makes them really, really versatile. In this case, we're going to specify that this pin is going to be an output. Whenever you're trying to figure out if your variable is supposed to be an input or an output, I like to think light, sound, or motion. If you're dealing with light, sound, or motion, more than likely it's going to be an output. Again, inputs are things like joysticks or buttons or other devices where you're taking in information. So the command to specify pin 4 as an output is pin mode, the name of your variable, then all caps, output. Pin mode, laser, output. All right, we have created a variable, we've specified it's an output. Now, we get to make it dance. So we want to turn 5 volts on and off, right? And so that's actually really, really easy to do. So like we said before, in the void setup, this code runs once. We don't need to continually specify this is an output, but we're going to test our laser by blinking it on and off, on and off, on and off. And so that we want to do in the void loop because we want this to loop over and over and over and over again. And so the first thing we want to do is turn 5 volts on out of pin 4. And so the command to do that digital write, laser, high. Now, you can kind of see this format is pretty similar. There's, kind of a command. There's something we want our variable to do, which variable we want to do it, and then what we want to happen. So you kind of see this similar format here. In this case, we have digital write. Now, all that means is I want to write some voltage to pin 4, and I want it on. So digital write, laser, high, is equivalent to saying I want 5 volts to come out of pin 4. Now, there are other commands that are very similar to this that we're going to cover a little bit later, but right now all we need to know is that digital write, laser, high will turn 5 volts on that pin that we specified earlier, pin 4. Now, whenever you tell a robot what to do, you have to tell it how long you want it to do it for. Robots are very, very logical, and so if you don't specify a time frame, sometimes you won't quite get the desired result from what you're trying to do. So delay 1000. Now, Arduinos, they can think very, very, very fast, right? We're talking millionths of a second. And so Whenever we tell an Arduino to wait or to do something for a specified time, we do so in milliseconds. So by saying delay 1000, I'm saying wait for 1 second. You know, if I wanted to do 2 seconds, 2000, 3 seconds, 3000, just like that. But for right now, we'll do 1000, right? You could also go way smaller, right? So you could say 500 for half a second. There's tons and tons of options. But for right now, we'll stick with 1 second. So I turned my laser on for 1 second. Now, I want to turn my laser off for 1 second, because this very first example, like we said, we just want to blink our laser on and off. Boom. So feel free to write that code out again. That being said, whenever you're writing software like this, there is no shame in copying and pasting, so long as you're making sure that you're changing your variables around. So in this time, I don't want to keep it on, right? I said turn on for 1 second and turn on for 1 second. I need to change this high to low, and low means off. So in this first line of code, I said, hey, turn 5 volts on pin 4. Wait 1 second. Send 0 volts to pin 4. Wait 1 second. All right, at this point, our code, our very first code, is complete. So this is all we need. And so we're gonna upload this code, send the code to the Arduino here in 1 second. But what we wanna do is we wanna make sure that we have a couple more things set up. So if you recall, right, we went back up to the Tools tab and made sure that everything was set. So whenever we're writing code for Arduino, we have to verify that our code is correct before we send it over. So if you have errors in your code, then Arduino won't let you send your code. And so here, I'm gonna show you something really fast. This check mark right here, I'm gonna click this check mark. It's gonna ask me to save my code. You can if you want to. I'm not gonna worry about it right now. Okay, and at the bottom of the screen, you can see that it is compiling. It says compiling sketch right here. It's gonna take a few seconds. And if everything is correct, then it will say done compiling. Okay, but check this out. Let's say I forgot this 1 semicolon. Let's say I go right here, I forget this semicolon right here. So I deleted that guy. If I hit verify, boom, my screen goes orange. You guys see that? Okay, now this is kind of weird because you see how this line is highlighted? That makes you think the error is here, when in reality, the error is right there. So if you do have an error in your code, you can either take the code straight from the flash drive that came with your kit, or you can go through the guide and make sure you're not missing a semicolon or something. But if it ever says, so if it says like error compiling, or it says expected this, or there's a bunch of other error messages you can see, then there's something wrong with your code. And so it's really important that your capitals are the same, and if it's lowercase, or you have your brackets facing the right way. And so it's really, really important. So you see, I'll put that semicolon back in. I'm gonna verify again. And now it says done compiling again. Okay, so that's one thing that could go wrong. Okay. So now, I'm gonna show you one other thing. In the Tools tab, earlier, we went through and we made sure that our board was right, we had this was right, and we had a check mark on our COM port. So once we compile our code and it's good to go, there are no errors, there's this upload button. Now in reality, if you hit upload, it's gonna compile your code anyways, so you could not click this check mark and just click the upload button. So I'm gonna do this right here. Ask me to save again. So now it is compiling the code at the bottom. Now you see here it says uploading and then done uploading. So it only takes a couple of seconds. Now that being said, I'm gonna show you something right here. So let's say there was an issue where I went to the Tools tab. I have Arduino Nano, I have the processor, but port. You see how I don't have any check marks here? If this port was grayed out, or you didn't have that check mark and you tried to upload your code, it will compile just fine, but then the screen will go orange again. Now this time it doesn't say expected this or error compiling. It just says problem uploading to board. So if you have this issue, your code may be totally right, but there's something wrong with your communication. So if this happens, go to the Tools tab, make sure you have all that stuff set the way we had it before. And if you do, it should be no problem at all. So if you wrote this code here, you have all that stuff set, you hit this upload button, and then it goes through the process. It says compiling and uploading, and then boom, done uploading. Then you're ready to go. And so at this point, if you did all that stuff correctly, you should see that your laser starts to blink. So now that we have our laser all set, it is time to get some data from our joystick. We're going to read that data from the joystick and then use that data to move our servos. Let's head back over to Arduino and write some code for our joystick. So if you grab this code from the flash drive, it'll be called Joystick Test. Now this is the exact same code that we have in our guide as well. So rather than write out all the code here, I want to just take some time to explain it here. So we have a very similar setup. We have a variable above our void setup. We have some information to help our code in the void setup here. And in the void loop, we have the main part of our code. So there are a couple differences here. Now, if you remember in our last code for the laser, we had int laser equals 4 because pin 4 was the pin that's hardwired in our circuit board to output our laser. Now, in this case, I haven't specified a pin, and there's a very important reason. So right now, I have one variable. It's also an integer variable, and I have named it joyx. In this case, standing for joystick X. Now, you could call this pan joystick, left-right joystick, really whatever you want. I usually go with X and Y because that's pretty common in terms of math or robotics whenever you have this sort of left and right, up and down kind of relationship. So there are two channels on the joystick. There's a forward, backward, and a left and right. And so we're going to start this code by just getting half of that data, one side of the joystick. So we're going to start with just side to side. Then we're going to add and build onto this code and eventually get both sides of the joystick. For this first example, to make it as simple as possible, we're going to get one channel of our joystick data working. So we're going to call this the X channel. So I have int joyx. All right, now in the void setup, this guy is different. We have serial.begin 9600. So how a joystick works is it's actually really fascinating. So I don't care if the joystick's in your Xbox controller or for some PC or you're using it to control a robot. All joysticks work the exact same way. You have voltage going in to that joystick. As you move the joystick forward, backward, left, and right, what you're doing is raising and lowering what's called resistance. So you're raising and lowering voltage. And it's that change in voltage that the Arduino is reading. So you move the joystick around, it's changing the voltage coming out of the joystick. And that's how you can take in that data. You can read that change in voltage. And then later we're going to write conditional statements, so like an if statement, based on where or what kind of voltage you're reading out of that joystick. And so because we can't see voltage, we need to have a way to see what the Arduino is thinking. And we do that through the serial monitor. So the serial monitor is something we have to initialize. And so to start up the serial monitor or to use the serial monitor in our code, we need this command, serial.begin 9600. Now here at 9600, don't worry about that too much. That's referring to the communication speed or the baud rate. All you need to know is that has to say 9600. Now, most of the time that number is going to stay the same. There are some crazier sensors and stuff that use different communication speeds, but for right now, we're going to keep this right at 9600. So this is what initializes the serial monitor, and the serial monitor is a really, really, really useful tool. There are a couple of ways to open the serial monitor. If you go to the Tools tab here, you can open the serial monitor by clicking this right here. Also, it says Control-Shift+M. Now, I think the easiest way is to use this magnifying glass here in the upper right-hand corner. So, serial monitor. If you click this, it'll open up the serial monitor. I'm not going to click it yet because we haven't really done anything. But this is how you start the serial monitor. Okay, now here's where it gets interesting. In our void loop. So, joyx. this is my variable up here. And if you remember, I did not specify what pin this was going to go to. And the reason I didn't is because I want the joystick variable to not only read data once, I want it to continuously read this data. And so, if you remember in our last code, we used the command digital write, and that sent out voltage. What's awesome is it is very easy with the Arduino to also read voltage. And so in this case, we're going to use the command analog read. So I have this variable. Because I have the equal sign, I'm basically assigning a value to this variable. So I have said the value of joyx variable is whatever voltage I read on pin A0. So we cover this a little bit more in detail in our guidebook, but the Arduino has analog pins and digital pins. I'm not going to go into too much detail right now, but in our last code, we used a digital pin because we just needed to turn voltage on and off. If I ever want to read a string of data, more than likely I'm going to use one of my analog in pins. And our joystick for this circuit board for the robotic laser cannon kit, the joystick channels are hardwired into pins A0 and A1. So since we're only trying to mess with one side of our joystick right now, I'm going to use pin A0. So again, the value of joyx is equal to whatever voltage change I read on pin A0. Now this next line is just printing that data back to me. So serial.println joyx. All right, now this is one that I see my students do all of the time. This looks like it might say print in with an I. It is an L. It is not a 1. It is not an I. It is an L. That's L for line. So serial, same command is up here. Serial.println joyx. So all I'm doing is I'm asking the serial monitor, which allows us to see what the Arduino is thinking. I'm asking it to just print that data back to me. So the value of that variable is whatever voltage you read. Then print that value back to me so I can see it. Because we need to be able to see this data in order to get to know what conditional statements we can write and in order to kind of build off of this code. Now I also put a delay statement in here, right? So, a tenth of a second, right? Because we're dealing in milliseconds. This number can change. It is not super important. It's often a good idea to put a small delay in there, and the value isn't super important. So that way the Arduino is not thinking as fast as it possibly can, because if I'm reading data every tenth of a second, that is more than fast enough, while kind of like keeping your code nice and organized and like making it so your data is really readable. All right, so once we have all of our code written, we are ready to go. So just like before, we want to make sure we compile our code, so we'll go ahead and hit compile. Sure enough, no errors. Under the Tools tab, let's take a second so we know our board is right, we have our processor still good, we still have that check mark right there. Then we are ready to upload. Okay. So our code is uploaded successfully. Now, the serial monitor allows us to see what the Arduino is thinking. And so again, we're not going to know if this is working until we open up the serial monitor. So I'm going to use that magnifying glass right there. And you'll see, I see the number 515, sometimes 516. Your number might be a little different, anywhere from like 510 to 520. But you'll see that as you move the joystick around, that number will change. So generally speaking, whenever I do an analog read of an analog pin, at one end, I'll see 0. So now I have my joystick all the way over to one side. 515, 520, 510 in the middle, and 1023 all the way in the other end. And so if I move the joystick back and forth slowly, we can see that I have a string of numbers. And so it's this string of numbers that I'm going to use here in a second to control my servo. But if you upload this code and you see this string of numbers and it changes as you move your joystick, then you are ready to go. You have a working joystick. Okay, so now that we know our joystick is working, we want to use our joystick to move around our servos, right? So servo motors are perfect for this little robotic laser cannon kit because unlike a standard DC motor that just spins, servos are very, very accurate. And so there are a couple different ways to do this. I think a lot of times you'll see other people use what's called a map command, and that would totally work for here. But because we want some accuracy, I want to show you guys a method with creating what's called a position variable. And what's nice about this is that as you move the joystick, the servo will move. But if you let go of the joystick, the servo will hold its position. And it's also very easy to speed up or slow down your servos. And so it's not too tricky. And so if you look at our code right here, this on the flash drive is called the position variable code. And this is the next step. And so we haven't added in our motors yet, but I wanted to show you guys how this works. So the very top of the code, int joyx, that's the exact same. But now we have a secondary variable. This is int position x, POS for short. So position x. Now I have set this at 90. This is just a number. I have created a number that later I'm going to use. Now the reason we make this 90 is that most servos have a range of motion of 0 to 180 degrees. There's definitely differences. Some are 270 and they're even continuous rotation servos. But for our servos, we have 0 to 180. And I want to start my servo always right in the middle, which is 90 degrees. So we're going to get into how you write that code later. But right now, I have 90. That is the value of my position variable. In the void setup, we're starting the serial monitor again. And in the void loop, I have a little bit more data here. So joyx equals analog read A0. That's the exact same as before. We also want to print out some data. That being said, check this out. We are no longer printing joystick X. We are now going to print the position X variable. Now, as I said before, servos move from 0 to 180 degrees. But if you remember, when we read the data from our joystick, it gave us the numbers 0 to 1023. Now, a servo cannot move to 1000 degrees. And so what we want to do is we want to create a more usable set of data to use later in the next code to move our servos around. So what I'm doing essentially is I'm looking at the joystick data, but I'm using the joystick data to make my position variable bigger or smaller. I will then tell the motor to react to the position variable. And that might sound totally crazy. This is a little bit more of an advanced concept, but we're going to go through this a couple of times. So right now, I'm reading a change in voltage on pin A0. That's the exact same. I am then printing the value of my position X variable. So right now, if I just uploaded this code, the serial monitor would print the number 90. Okay, so when I move my joystick around, I got the numbers 0 to 1023. And so here I have my first conditional statement. I've said, if the value of joyx is greater than 800, do something. And the reason I choose 800 is because I want to move my servo forward when I push my joystick forward, or left or right, it doesn't really matter. But if I read 1000 all the way to one end, and 500 in the middle, if I happen to read the number 800 or go above it, then I must have my joystick in one of my positions, either all the way left, all the way right, all the way forward, or all the way back. And so that's what I make my condition. I must be moving my joystick past the middle, right, and aiming in a certain direction if I happen to go above 800. So you could do 800, 850, whatever. I don't like using anything above 1000 because that can make it all too sensitive. By using 800, you create what's known as a dead zone in the middle, and it makes it pretty accurate. But let's move on to the actual body of the conditional statement. So I've said, read the voltage on pin A0. if you happen to read above the number 800, add to the value of position X. Now this is kind of weird. Position X plus plus. Now, all you guys need to know right now is that whenever I have plus plus in code, in actually most programming languages, that is a shortcut to say add by 1. So add 1 to the variable position X. So if I move my joystick forward, the value of position X starts at 90, but it's going to increase by 1 as I hold my joystick forward. So I'm holding my joystick forward. It's going to go 90, 91, 92, 93, 94, 95, 96, 97, 98, and go all the way up. But it's going to do this every 25 thousandths of a second. And so it actually counts up and down pretty quick. So I'm making my number, position X, start at 90, but then move up as I move my joystick to one side. Now, like we said before, the joystick, whenever you do a straight up analog read on that pin, you get the number 0 to 1023. So in the same way, if I happen to read less than 200, I must be putting my joystick in the opposite direction. Because again, 500 in the middle, 0 is all the way over, so 200, if it goes less than 200, then I must be moving my joystick in the opposite direction. So minus minus means the exact same thing as plus plus, except it's take away. So take away 1 every 25 thousandth of a second. So what's so cool about this is if you stop moving your joystick, the value of position X stays where it was. So eventually our motors will stay in their position. And what's so cool too is that if I think my servos are moving too slow, I can make this number smaller. So if I change this delay to 10 thousandths, it will count faster. Therefore, my motors will move faster. So I think the easiest way to see what's going on here is to open up the serial monitor again. So check it out. We have position X. So take a second, write this code. Again, you can just take it from the flash drive. I think it's a really good idea to write this code out and get that practice, but position variable is the name of the code if you want to just grab it. All right, so I got my port set. I'm gonna go ahead and upload this code. Compiling, uploading, done uploading. So I'm gonna open up the serial monitor one more time. So remember, last time I moved my joystick with the previous code, I saw the numbers 0 to 1023. But now, when I open up the serial monitor, sure enough, 90. Because at the very beginning of the code, I said the value of position X is 90. So when I print position X, it prints 90. But now, I'm gonna move my joystick left and right. So you see how my number is getting bigger? Now it's getting smaller. And if I stop moving my joystick, that number stays where it is. So I have lots of control over this variable here. And so since a servo can move 0 to 180 degrees, I now have some really good data that I can use to move my servo around. So this is the difference when you add in a position variable. You gain a lot more control over what your joystick is going to be doing. So our next step is going to be adding in our servo. That's going to react to the position variable, and then we will be able to move our servo with our joystick. So adding in a servo is actually really easy. So again, if you're grabbing code from the flash drive, this code is going to be called servo test. And so you'll see that a majority of this code looks the exact same. If you want to just add the changes into the code you had before, you totally can. Or you can open up a new code window. But let's take a second and look what's going on here. So again, like we said, servos are really useful for setting position, and there are a few key things that you have to include in your code when you want to use a servo. So the very first thing is this #include servo.h. So servo.h is what's known as a library file. What's nice is when you start making more complicated codes in Arduino, oftentimes you'll pull in what's called a library file, and that's a file that works in the background. And it makes it so that instead of hundreds of lines of code, you can make your code like 10 lines of code or 15 lines of code. And so it's really important background information. And so hashtag include. That command is essentially saying, I want you to search for and find and include the file servo.h. All right, now unlike LEDs and lasers and other things, whenever I want to declare a servo, I need to use this syntax. Capital S, servo, then the name of my servo. In this case, I'm gonna go with something pretty boring, servo x. Now you could name this variable whatever you want. I chose servo x because it's rational, it makes sense. So I have capital S that declares a servo, then I have the name of my servo. These two variables right here are the exact same from the previous code. I'm starting up my serial monitor, but you'll notice up here for the servo, I haven't declared what pin I'm going to use for my motor. In this case, I have servox.attach. Attach is the keyword here. So attach is how we specify what pin we want to use. In this case, we're going to use pin 3. The servos for this robotic laser cannon PCB are hardwired into pins 3 and pins 5. So we're going to start with our first servo. We have the name of our servo, servo X, attach to pin 3. Okay, so we already saw in our last code that when I move my joystick forward and backward, I am making the value of position X bigger and smaller. So what's so cool is we only need to add in 2 lines of code. And it's the same line for both sections. So if I move the joystick forward, make position X bigger. Servo, right or move to whatever the value of position X is. So I'm making position X bigger. Servo, I want you to respond and move to whatever degree that number, position X, happens to be. If I move my joystick backwards, I want to make position X smaller, and servo, I want you to respond to whatever position or degree the value of position X is. And so, let's see, we added 1 line of code, 2, 3, 4, 5. With 5 lines of code, we can go from just seeing numbers to actually having our servo move back and forth with our joystick. So let's go ahead and we will upload this code. Compiling. And oh, problem uploading. Let's see. Sure enough, gotta click that COM port. Uploading and done. And so now, as we move our joystick forward and backward, we see our servo responds accordingly. So again, if you let go of your joystick, that servo is going to hold its position. So you move your joystick forward and backward, and then you have your servo working. So if your servo starts to move, you are good to go. Just in case your servo isn't moving, you might want to check that you have the orientation correct. On the circuit board, it's kind of small, but you see there's a negative and positive. And again, this has gone over more in more detail in the build video as well as the guide book. But you want to make sure that the brown wire of the servo is facing that negative, is plugged into the negative side there. Because again, if you wire up your servo backwards, it's not going to move. But if you had that correct and your servo starts to move, then you are good to go. All right, so we have one servo responding to one half of the joystick. Now we are going to basically double our code. And so this makes our code seem way more complicated, but in reality, as we go through this last code actually, I want you guys to keep in mind that all we've done is double what we had before. So we want to use another servo, and we want to take the other half of our joystick data. We're also going to need to create another position variable, but they're all going to function the exact same way. So if you look over here, I still need the servo library file. This is how I would add in a second servo. So I still need to type capital S servo, in this case, servo Y, which makes sense. I now have a joystick Y, a position Y variable. I have a joystick X, a position X variable, and I've also added back in my servo. One thing that's awesome about Arduino as well is that it's really easy to combine codes together, and that's a great way to build your own projects. You can take a little bit from here and take some from over here, and even this code itself. I don't want to make this video 10,000 hours long, so we're going to stop after this one. But even in this example, at the end of the video, I'll talk to you guys about some more things you can do to even switch up this code here. So we're adding in our laser. We've still got our serial monitor beginning, right? We have initialized it. We're not really going to need it at this point, but you know, it doesn't hurt to have it in there. As we said before, the laser cannon PCB that we use for this project has the servo wires hardwired into pins 3 and pins 5. We have to specify that our laser pin, pin 4, is going to be an output. Now, here in the void loop, I have digital write laser high. Now, these little joysticks right here have a button. You can click down, and you use this all the time in like video games. You know, you can click down on the joystick to do all kinds of other functions. I'm not going to cover the code that you would need to get that joystick data or the button data from the joystick in this example. But I hope to have a guide out soon with some more tutorials about how to take this further. But for this video, I'm just going to have the laser on. The laser stays on while you are aiming this laser. It's really fun. Like I like showing my students how to click the button to fire the laser, so that way the laser only fires when you click the button. But in terms of ease of use, it's actually easier just to have it on the whole time. So that's the first thing I'm going to do is turn that laser on. And again, if you're interested in that, keep an eye out for that next video, because I have a bunch of videos planned for this robotic laser cannon kit here in the very near future. So the first thing we did in our void loop was start our laser. All right, now, if you remember, I have the analog read command. So that's reading a change in voltage. This time, I'm also reading a change in voltage on pin A1, so A0 and A1, because those are the pins that are hardwired into the circuit board for our joystick. All right, now, I have my if statement. Now, before we had if joy X is greater than 800, make position X bigger. Servo, respond to position X. But you'll notice I also have a secondary condition in here. And if I were to translate this code from robot into English, I would say, if you read a number bigger than 800 on the joystick, which means it's pointing to one extreme, like either left or right or up or down, make this number bigger, but only if that number is less than 180. And so what this part does is this sets in a condition. So now as I move my joystick, position X is going to get bigger, but once the value of position X gets to 180, which is the maximum for the servo, it's going to stop because it can't meet both conditions. And so by adding in this secondary variable, you'll notice if you don't have this, you can move the joystick forward. And as you move the joystick forward, it's going to go 90, 100, 120, 130, 180, 190, 200, 210. If you keep holding the joystick down, if you were to open the serial monitor, you'd see the position variable, that number will get giant. And so the servo will stop responding once position X goes above 180. And so it can look like your servos are broken, but it's just that the number is too big. So having this secondary condition in here, make sure that your number doesn't ever get bigger than you need. This second conditional statement, right, is the exact same as before, but now I've said, hey, stop if that position reaches 0. So move position X smaller, but only if that value is above 0, because we can also make the position variable a negative number. If we keep holding that joystick all the way down, that number is going to go negative. And obviously a servo can't go to negative degrees, so it's not super useful. And now this second set of conditions right here is the exact same. It's just for my other servo. So if joystick Y goes greater than 800 and position Y is less than 180, make position Y bigger and servo Y go to position Y. And so as you see, even though this code is twice as long, I would argue it's not twice as complicated. It's just basically doubling things up. So at this point, your code is done. You can move both joysticks around and the laser is on, and there's a bunch of fun stuff you can do with this. I have a little laser target PCB that we're gonna have up in the shop here pretty soon. You can use this to annoy/entertain your cats and dogs, or really anything else. And so what I love about this kit is it's a great way to talk about reading analog data and controlling servos. So like in my class, we use this joystick data with servos to do things like robotic arms, or this laser cannon, or there's so many things. And so you can also use joystick data, to control robots and robots that drive around and really anything. So keep in mind that you can take this kit way further than what we covered in this video. I hope to have some more tutorials up really soon about getting the button data from the joystick, or maybe even using the map style commands. And keep in mind, on this robotics kit, we include the NRF Nano, so it's the Arduino Nano with a micro USB plug, but also has the NRF 24L01 radio plugged in. And there are tons of great tutorials out there, but I hope to have one of ours up really soon. So this Arduino with our kit, even though we didn't cover wireless communication, has the ability to take data from another radio and another Arduino right out of the box. And so we also have this universal wireless controller that we're really excited about, that we hope to have on the store here very soon too. By the time we get this video out, we might even already have it up. But that is coming soon. And so we also have a really awesome little robot coming that can be controlled with the same radio controller. So we have lots of stuff in the pipeline. Thank you guys so much for watching. Remember, we started ACBR, Anyone Can Build Robots, because we believe it. Anyone can build robots. And that's why 25% of all of our sales go to giving these kits away for free. We want to raise as much money as we can by selling these kits on Amazon or on our website, so that way we can bring the joy of robotics to students all around the world. So if you did purchase one of our kits, thank you so much. If you watch this video, you get this tutorial, check it out, As a high school robotics teacher, I spent a lot of time doing research, and all of these projects are tested in the classroom, so they're high quality, also almost it's just about as low cost as they can possibly be. So that's one of our mottos here, that we want this to be low cost, not low quality. So thank you guys again so much for watching this video. Have a great day.